So thank you very much for having me here. I'm very bummed I'm not there. I'm actually pretty jealous. I would like to be there. So usually I'm at the Australian National University, and I'm funded by the Australian Research Council. That's like the equivalent of NSF. And what I've been talking, I will be mostly talking about our approach and philosophy in undertaking this problem. Unfortunately, I won't have much results to show you, but I'll try to convey what's our main approach and how we are trying to attack this problem. So the main problem is, as other people have talked about, is how we need to parameterize unresolved scales in climate models, and in particular I'm focusing on the ocean mesoscale eddies, which is all these circular features that you see here, that are like all over the North Atlantic in this video that I'm showing. This is like a very a video I really like, and it has been popularized recently in the recent Nobel laureate ceremony. So trying to understand how to parameterize all these circular eddies is the name of the game. Before I move on, I want to pay a very, very special attribution to my friends and collaborators at MIT, in particular Greg Wagner and Adeline, but also the rest of the group at MIT, Raf, Adre, Shoujo, and also special thanks to Stephen Griffiths for helping out and talking with me in various points in time. So here's something that illustrates sort of the problem and why ocean eddies bring about headaches. So this is surface ocean currents as modeled with three different global ocean ice sea ice models at three different resolutions, lateral resolutions. On the left, we see how the ocean is modeled when you're using a 1 degree resolution, and on the far right, we see how the ocean looks like when we're using a 10th degree of resolution. And the picture on the right looks much more like the video I was showing you in the beginning, and also much more like how the ocean actually looks if you look of the ocean currents, via satellites or something. So the problem is that the headache comes because what we typically use for making climate predictions is models that look like the one on the left and not the ones that look on the right, because of computational costs, and because these models are so costly to run. You cannot run them for hundreds of years forwards and under different forcing scenarios to produce climate predictions. So if you look at this in like a first glance, you will say, oh, how do these people sleep at night? Is this the ocean that the climate predictions are having in this laminar, not realistic at all ocean? And that's like a first concern. But what we are really focusing in climate science is that we're not really focused on knowing exactly how each eddy behaves and where each eddy goes. What we're really interested is how all these eddies collectively affect the low order long time statistics, which is the climate. So missing out eddy features is not a big of a deal, but what we really want to make sure that we accurately capture, as accurately as possible, is the collective effect that all these small scale eddies have on the large scale flow. Just to bring a bit, so this is apparently a section of the ocean that I'm quite familiar with around here. This is the East Australian current, and just to bring you a little bit in my neighborhood, this is where I usually live, in a small village at the coast of New South Wales. which is hopefully, fortunately, accurately captured in all resolutions. So just to bring a bit of perspective, I don't even know if I have to comment anything here, but that's the state of the affairs that we are at. And whilst both are beautiful, ideally would like to have things like on the right, but even if we can have things like on the right, include their effects on the large-scale flow. That's what we're trying to do. So, in other words, what we're trying to do is we want to make the coarse model, the model on the left, feel the effect of the flow details that it's not resolving. And this is what people have been calling eddy. This is what we refer to as eddy parameterization, and a lot of people have talked about this in the morning. But just making this point again, we're not in climate science, at least, and because we're not really doing any weather prediction. We're not interested exactly on where each eddy is at in a week's time, but we are interested in the collective effect of all the eddies on the large-scale flow, and that's the main difference between if you're interested in climate or if you're interested in weather and how the ocean or the atmosphere will evolve in the next week. So how this talk will go is I'll give a little primer how eddies affect the large scales. And this is not, I'm asking for forgiveness from the oceanographers in the room. This is not tend to be a lecture on, eddy mixing and isopycnal mixing, but just to bring everything at the same page. And mostly I'll use this as an example to demonstrate how in our approach we feel that we think we can take current parameterizations and improve them. So before starting talking about that, I just want to bring everybody in on the same page. So one thing that one important concept is the concept of that eddies move tracers, move heat, move carbon along neutral directions. And what are these neutral directions? Directions where density is constant. So imagine the scenario that isopycnals, or surfaces of constant density, are slanted, and in the ocean and in the atmosphere in general, they do get to be slanted a lot of times, and because of the Earth's rotating, in a sense. So if you have slanted isopycnals like that, and you try to take a parcel of fluid and move it up or down, it will find itself in an environment of different buoyancy, and this buoyancy will tend to push it back to where it came from. The same thing if you try to take a parcel of a fluid and move it left or right, because again it will find itself in an environment of different buoyancy, either lighter fluid or denser fluid, and buoyancy then will tend to push it back to the surface, to the constant surface, to the constant density surface it started from. So, bottom line is that if you try to take a fluid parcel and move it along a surface of constant density, that's the direction that you will feel less resistance. So, in other ways, because moving a fluid parcel in that direction does not require paying any potential energy, so it's much easier to move fluids along surfaces of constant densities. And that's what, in essence, eddies are doing. They are moving and mixing tracers along surfaces of constant density. And if we go back to how a tracer, you can think of heat or temperature, evolves. It follows a usual advection diffusion equation. And then if we decompose our fields into what we resolve, which I color with blue, and what we don't resolve, which I color with red, then we can rewrite this equation as an advection diffusion equation for the resolved flow. This is what our model will be doing, plus this red term, which is what people call subgrid, eddy fluxes, or there were various names. This is the term that our model doesn't know. And if we have some magical way of prescribing this term, then our model for the blue will be perfect. This in this context, these are called the eddy tracer flux. This is the red term here. So what an eddy parameterization is try to express the red term, the eddy tracer flux, in terms of all the blue fields. I mean, and I think a slide like this has appeared in almost any talk I've seen up to now. And what we can use physical intuition to infer what this functional relationship might be, or we can use a neural network, or anything really. But that's the name of the game. That's the name of what we call parameterization. So like the simplest way to parameterize this eddy tracer flux is to parameterize it as a down gradient, it's like a down gradient large scale, as a down gradient flux of the large scale tracer. So doing this is like I mean, if we do try to approximate the eddy tracer flux as the minus of some positive number here, of minus of the gradient of the large scale tracer, then this makes this term on the right hand side that we didn't know be like an eddy diffusivity. And so that's like, since as we discussed, like that eddies tend to move and mix tracers along isopycnals, then that's kind of like, okay, then what eddies are doing are just like making things more diffusive. Then you can start being a little bit more elaborative and don't describe as a diffusivity that is the same across directions, but differentiated in the horizontal and the vertical. And then you have like the eddies mix differently in the horizontal compared to the vertical, but still, if you have slanted isopyclas, as most times we have in the ocean, you still tend, if you do that, you still tend to mix across isopycnals, and that's not really how the eddies work, because this requires moving fluids of across surfaces of different potential density. So a more and this is what the Reddy and the Genn-McWilliams parameterization is like make this a little bit more elaborate, and instead of having have here a tensor which tends to rotate first your coordinate system to make it parallel with your isopycnals, and then apply some diffusivity along isopycnals and no diffusivity across isopycnals. So that's the usual notion of isoneutral diffusion, as we call it. And there's like two components of that. We have like a skew flux, which is what we call Genn-McWilliams diffusivity, which is trying to model how advection steers tracers along isopycnals, and we have the other component of this tensor, which tries to model how tracers are diffused along isopycnals. I mean, this was developed back in the early 90s, late 80s, early 90s. Then it took, and despite that I've said this in one sentence, like just convert to a coordinate system that is parallel to the isopycnals. That took a few years to implement. I mean, it's quite tricky. And a big portion of the literature was developed in exactly how to implement this diffusivity tensor and how to implement this rotation into isopycnals. Don't forget that isopycnals move up and down all the time, so you have to at every time step you have to recompute how are my isopycnals now and how I need to rotate and where do I need to apply, in which direction I need to apply this diffusivity for this parameterization to work. And there are more other problems with this type of parameterization. So, for example, we know that on the interior of the ocean, indeed, eddies tend to mix along isopycnals. But as we approach at the top of the ocean, there's this so-called mixed layer, which is driven by turbulence of the boundary layer, and the ocean at the top is fairly mixed. And in that part of the ocean, tracers tend to mix across isopycnals. So somehow this parameterization, as we approach the top, has to change to a different type of parameterization. That's one problem. Another problem that comes up is that this sort of isopycnal and isoneutral diffusion has to turn off when isopycnals become too steep. This is very much related with as we are approaching the top, the isopycnals become infinitely steep, and usually this second part is done is implemented in ocean models with if statements. So if the slope is more than something, then turn it off, and or there's like what people are called slope clipping or slope tapering, and it's actually this is an important part of the implementation of the parameterization. If you don't include that, then you get nonsense. Other issues with this sort of parameterization is that the eddy size changes with latitude. So for a given model resolution, we might be able to resolve eddies at the tropics, for example, and then not resolve them far out at the poles. So the parameterization should not be on in regions where we actually resolved eddies, because then we'll be double counting for the eddies. So then we go into things like scale-aware parameterizations, and there's work done on that aspect also. This is not trying to be like a thorough review of what's been done. I'm just trying to use this example of isoneutral diffusion to then use it as an example to how we can improve it in a systematic way and how we can move forward. Other issues is that the activity changes. It's not the same everywhere in all regions. There are regions of high eddy activity, especially near western boundary currents in the ocean or in the Southern Ocean, and there are other regions which are more quiescent in eddy activity. So if you are going to put a Genn-McWilliams diffusivity, that should probably not be the same everywhere in the ocean. So and possibly that could have some space or depth structure or time or changes with season possibly. So all these are things that people have been thinking about. Now, how do we go ahead and come up with a new parameterization or improve some parameterization? Let's. So firstly, we get inspired by data. So data could be observations, could be model output, could be just looking at the night sky, as like the astronomers of the medieval centuries were doing. They were just watching the planets go round and around. And then we can use our physical intuition or the known physics to derive a model to describe observations. This model will have, with most of the times, have some free parameters, like for example, Newton came and gave us the law of gravitation and the laws of motion, and there's like a couple of free parameters there, or one, like the gravitational constant. Then we can go and, go back at the data and calibrate these free parameters so that it best matches our data. And after we're done, we can put it in the climate model, or and then try to go along with that. So in the era of machine learning and with increasingly high computational capabilities, where machine learning can come into this, it can come into the left two parts. So instead of us looking at the night sky, or it's like people looking at model output and trying to figure out the patterns, like machine learning can do that for us, and then algorithms can go through all the available data and figure out the patterns, and then we can somehow infer from that patterns new dynamical laws that could best describe these patterns. And then again, machine learning can help us calibrate the parameters, or any parameters of our physical model in a systematic way and across various different scenarios, so that we find one set of parameters that best capture all possible scenarios, and then we can implement it in a model. So that's the state of affairs we are at now. So what about the title? Let us go back to what I was saying, towards a data-driven parameterization for the mesoscale. So I just wanted to discuss, because some people, often the notion is that if you say you're doing something data-driven, that has to involve a neural network. So in my head, that could be the case, that could be one case, but anything really that is inspired by data or by observations is data driven. So what we're trying to do in this work is instead of going and starting from a neural network, which involves like 1 million parameters or more, and try to calibrate all those to best match the observations with our model output, we start from what we currently have, like a parameterization with 2 or 3 different parameters, and we try to calibrate that well enough to see what's the best that parameterization can do, and then add more physics, which includes adding more free parameters possibly, and recalibrate and see how well we can do with that. And in this recipe, it's the calibration that is mostly the data-driven component. And so I wanted to talk a little bit about calibration here. So when we are calibrating parameters, so everybody agrees that calibration is great, but usually it's not really done in a systematic way. People have worked on that, but in my experience, when I ask, okay, so what's the, we're running this 1 degree model, what's the GM coefficient? People, respond to me with their favorite number. They say it's 500, 600. Some other might say 1,000, or they have a scheme that varies with latitude. And it sort of reminds me the way that my grandmother used to tell me recipes, you'll put a little bit of sugar, some sugar. There's no really a systematic way of getting that number out, and that's what we are. I understand that that's very cumbersome to do, systematically calibrate a model and figure out the best parameter, across different forcing scenarios, but I think that's kind of required. So the good thing about what I'm trying to I will try to discuss here is that So one of the very big difficulties of calibrating is that you usually need to have the adjoint model of your model you're trying to calibrate off. And that's really, first of all, you don't usually have it, this adjoint model, or if you have it, it's quite difficult to work with. I'm not making this up. I've seen students arranging meetings with their therapists because of the adjoint MIT GCM model. So the good thing is that we don't really need an adjoint model, because what I'm suggesting we use is that there's these new techniques for Bayesian optimization, which does not require any adjoint model, is derivative free, and uses essentially ensemble Kalman filters, and that's what we are using to calibrate parameterizations. So let me talk a little bit about that. So ensemble Kalman inverse process is.
Sorry, Navid, you have about 5-6 minutes left.
Yeah, sure. So this is like a way to it's a derivative-free optimization method to find the optimal parameters in an inverse problem. So if G is our model, our ocean model, and theta are our diffusivities, and Y are our observations, this model will, with only just running your model forward, can with a few iterations find the best values of the parameters, the best value of your diffusivities that will make your model output match your observations. So, and like we are able to do that because of software that we've been developing. So first of all, we have a very good, fast ocean model that runs on GPUs and very flexible. And then other packages that implement these ensemble Kalman processes or blend these two together and allow us for calibrating parameterizations. So I'll just demonstrate this in a very simple problem. So the problem I decided to use here as a demonstration is mostly as a demonstration, not that we're trying to solve the mesoscale problem with this. I just want to demonstrate you how this calibration works. So I have this baroclinic adjustment of the front. On the left, you see buoyancy. You start with like a sloping the isopygnals are pretty steep, and as we let this go, as we let this go, this front will become baroclinically unstable. On the right, you see it's the same setup, but you just see a tracer initially just be where the blue thing is. So as we let this go, you see that the front becomes baroclinically unstable, eddies form, the isopygnals slump a lot, so they are not as steep now. So this is what the parameterization should try to encapsulate. So somehow the eddies made the isopygnals slump, so that's what ideally we want our parameterization to be able to capture. So here I'm showing you a 2D version of this, of the same problem. So there's no eddies at this time because this is just a zonally average. There's no longitudinal extent. On the left, I'll show you what happens if I don't include any parameterization, and on the right, I'll show you what happens if I include some GM and some ready diffusivity. So when I run these things, so on the left-hand side, the isopygnals remain steep as the way almost as the same as the initial conditions. While on the right-hand side, we can see that this diffusivity, this eddy diffusivity, made the isopygnals lean down a bit, and that's because eddies were created from the available potential energy that these isopygnals had. So this made the isopygnals slump down. Now I put two numbers. So I mean the name of the game now is to go and calibrate against the 3D model and find the best values of these parameters. And perhaps I should move forward a little bit. I'm just trying to show you how this ensemble Kalman inverse problem process really works, and here I'm demonstrating it with, I'm just creating observations with a given parameter values and then trying to close my eyes and see if this process can figure out the parameter values. And here, this is the summary. If I start from, like, my red lines are the actual parameter values that I use to make my observations. So if I start with an ensemble of models all over the place, after a few iterations of this ensemble Kalman inverse process, everything, all models, all parameter values collapse into the actual true value that I use. So this gives hope that you can use, I mean, this was like a made-up example, but then we can use them with observations coming from the 3D model or from realistic simulations to find the best value of parameters. So what I was trying to describe here is that we can easily calibrate free parameters of a turbulence closure, and we can even calibrate simultaneously across various scenarios to find the best parameters that work for all scenarios. And then with this method, adding depth dependence or time dependence on the diffusivities, for example, or any free parameter is trivial. And most importantly, by construction, a parameterization constructed this way is also numerically stable because it has been constructed by solving the parameterized model forward. But what's more important is that, like, now we can use this, like, we can use this loop and then have, use data from high resolution models or from LES or from DNS and gather observations as our ground truth, and then use our physical intuition to enhance parameterizations. For example, enhance the current parameterizations by adding more physics instead of if statements. And then possibly we do that, this will add new free parameters. Then we can calibrate all these parameters robustly and see if there's a value for this new parameter that is the same across all scenarios. Then this means that this new parameter we added is something that describes physics well. And then reiterate this process. And when all this converges and then the parameterization is very close to the truth, then we can implement it in the model. No worries about numerical instabilities or whatnot. So that's what I was trying to convey here. So I'll leave it here. Thank you very much.
Thank you. Questions for Navid? Yeah, Katie?
Yeah, Katie Dagan, thank you so much for your talk. I guess I want to come back to this concept of the best parameters that you've mentioned a couple of times, and I'm wondering if you have thoughts on when that might not be possible. For example, I work a lot with terrestrial biophysical models, and I'm not convinced that there is one best set of parameter values that works, especially in a global model. So I'm wondering if you have thoughts on how we can use machine learning to produce distributions of parameters, or when we want to look across both external variability and internal variability within a more complicated system, and how we might get around to that issue of not being able to find the best set of parameters. Thanks.
Yeah, so do you still see my screen, by the way? I just exit full screen so I can see people. So I guess what you're saying, that you have that there is a model in mind, and then there's not one parameter that works for all the globe or all regions. That's what you were saying. So how can
yeah, that's correct. Yeah, which I think is common, especially when you're looking at very heterogeneity and in a global context, and not just a particular region. But yeah.
And maybe I can just on top of that, right? So you've been talking about GM as one parameter, but it's actually a full field, and it's not obvious that observation can constrain it. So I think even if you're not inland, even for the ocean, it's unclear that you have actually a perfect set of parameters. So I'm kind of adding on top of your question. So yeah, how do you do that?
Okay.
Right? So how do we know what's the best when we don't know there is a best?
Yeah. So when I said when I was saying parameters, like a parameter could vary in space also. So it could be, it could be a whole field in my abstract saying notion of saying parameters. So for example, if you have a model that includes one free parameter, and it doesn't work as well in the whole globe, then you can extend that to be a field that depends on latitude, and you can recalibrate robustly. You'll find some answer, which is I don't know, some function of latitude or something. If you can make sure that, like, with different scenarios or different forcing or at the different conditions, the calibration gives you the same, more or less the same answer, that means that your underlying model is good enough that it captures what's actually happening. So so this means that your calibration is robust, and then your model captures what's actually happening. If with any little change in your initial conditions or in your model setup, you end up with a different optimal value for your parameter, then I think that means that you have to go back to the drawing board and rethink about your model, your parameterization model. I'm not sure if that answers the question. But the calibration process could hinge you towards whether your model captures the physics it supposedly it's there to be capturing, if or not. Was I clear? I'm not sure if I would have been accepted this answer I gave, but I don't know.
Sort of, yeah, I think so, yeah. Yeah, I see yes and no's. So I think either way, I think, yeah, it might be a longer conversation. But anyone else has any questions or comments? So maybe I'll follow up on that for a minute. Because I think this is something that is always a little bit tricky. You're talking about, one process with optimizing a set of parameters, but I think, in most cases, we're working with coupled climate models where you have tons of parameters and they all interact with one another. So, what would be your strategy then? Are we gonna do this kind of calibration for every single, parameter and then find this optimal space? That can be probably expensive. Not. Or is that the best solution, really, when we're talking about climate models, right? We have parameters for, things for land, atmosphere, oceans, and each one of them has its own set. Do you have a...
Well, okay. Yeah, my thought is that, okay, we can, we can take one component of that, for example, and then, for example, take, I don't want to give a particular example, but take one component of the model and try to calibrate that over different scenarios. Say that's like a model for the boundary layer, turbulence in the ocean. Try to calibrate it over, it has say it has 3 parameters. Try to find the optimal value of the parameters under different wind conditions, different stratifications, different anything you can think of, mean currents. If always the answer is the same set of optimal parameters, this sort of implies that your underlying model has captured what's happening. Then you should be happy with those parameters and you can move on. You can then, if you have then another parameterization, you can calibrate them simultaneously. So calibrate 2 parameterizations simultaneously. But it will be good if you already have a good set of optimal values for each one. Then you can start from these optimal values and see that if you're calibrating simultaneously, the system takes you to a different set of optimal values, and step this up step by step. I'm not sure if I'm answering. I think that's what you were asking, right?
For your thoughts on how to do that.
Yeah.
Models. Thanks. I appreciate it. Pedro.
Yeah, just building on Laura's question. So also, if you change the resolution of the model, then what would be resolved versus what should be parameterized would be different. So I'm wondering whether you think that coefficient would also change under those conditions. This is something we are thinking about in our gravity wave project, but also might apply here. So to what degree do you think these coefficients would change when you also change the model resolution?
If your underlying parameterization, like for example the GM diffusivity, that you know the simplest version of the GM diffusivity I was described has not any way of knowing what the model resolution is. Then you know, as you increase your model resolution, it won't change, but they should be changing. So somehow your underlying parameterization has to have a way of knowing what your model resolution is, so that these parameters change self-consistently as you increase model resolution. So that's part of the drawing board kind of you know, that's part of this this part of the game here. I don't know if you are looking at my screen. So does this answer your question? Or I don't have the answer for the problem you're thinking, but I mean, that's if I'm honest, but I don't even know if you're thinking of a particular problem, but that's how I would go about. So probably the parameterization has to be reformulated so that it has a notion, it knows what the actual resolution is, and that's sort of what's you know, what, like for the notion of mesoscale, what's happened with the scale-aware parameterizations, and you know, that's one way of doing it, and perhaps that's their way.
Okay, thanks. Any final question before our break? No? Okay, so let's thank the speaker again. Thanks, Navid.